All right, today we talk about proof structure, which is really quite an important day for us because here today we really do begin to give proofs. Now, we won't give complete proofs yet. Instead, all we'll do is set them up, but that is an essential first step. So here we go. I said to you at the start of the class that this is a proof class, but I also said to you that I really can't tell you what that is now. So today we really begin to get a good sense of what precisely a proof is. So, like I said, I will acquaint you with that common structure that all proofs share. And this goes all the way back to Euclid's Elements. This is precisely how Euclid did them. So let's learn how to set up a proof. And then tomorrow, actually, in the next section, we'll begin to give proofs. So, first of all, let's define a term. The term that we wish to define is theorem. Well, what is a theorem? A theorem is a statement that has been proven true. So, do note that a theorem is not a statement that could be proven true. Sometimes students will misuse it in that way. Notice the past tense here. A statement that has been proven true is a theorem. So if it hasn't been proven yet, even though perhaps it could be, we will not yet call it a theorem. So every theorem in this class, that is every theorem that we ever will have proven, is a conditional statement. So here are some examples. And I said this before in the previous section that what we prove in this class are ultimately conditional statements. So now we say in this section, once we've defined a theorem, that every theorem is conditional. So here's one. Linear pairs are supplementary. That is, if a pair of angles are linear, form a linear pair, then they are supplementary. Here's another. A second, vertical angles are equal. That is, if two angles are vertical, then they are equal. We will prove in a later chapter, those first two we'll prove in this chapter. In a later chapter, we'll prove that equilateral triangles are equiangular. That is, if a triangle is equilateral, then it is equiangular. Oh, and then here's just a fourth example for you, something that we'll prove near the end of the first semester, an extraordinarily important little theorem. If we take a triangle and join the midpoints of two sides with this segment, of course, then that segment is parallel to the third side. Okay, so these are examples of theorems that we will prove, will have been proven by the time the class is done. And these are all conditional statements for sure. Okay, so now let's talk about how it is that we set up a proof. And this is done in the same way. So write the statement to be proven in conditional form. Typically we do this, though later on in the class sometimes we get a little quick and because we're so familiar with it and don't do it. But here at the start we'll certainly do that. And then we also typically draw and label the diagram to illustrate the given. Okay. This is something you'll get used to because we'll do it all the time. We almost always do it. Now, there are a few proofs where this really isn't necessary, proofs where the point made is sort of more numerical than it is geometrical. But when the theorem that we wish to prove is really geometrical in nature, then what we do is draw and label the diagram. That is, we have specificity. We have a particular specific diagram in front of us with which we work. And then after we draw that diagram to illustrate the theorem, we write the word given on a new line, and after that, the word prove. And after the word given, we write the given of the proof, which really is, for that particular diagram, the given of the conditional statement that we wish to prove. And then what comes after the word prove is the conclusion. And these, again, let me emphasize, will be specific. Okay, we won't talk in generalities about, say, vertical pairs or something, but instead we'll talk about a particular vertical pair that is found in a diagram that has been drawn. So, conditional form, okay, we know how to handle that. That is, we take a statement and write it in if-then form, and we make sure that the result is synonymous with the original. So the vertical angles theorem, it will be called, says that vertical angles are equal. And what that really means is that if two angles are vertical, then they're equal to one another. And then step two, we draw the diagram, which is what we will reason about, what we will use actually in the proof. So our proofs in this way will be specific. And let me just make sure that you understand what this would be, right? So let's say that we were asked to prove that if two angles are vertical, then they are equal. Well, we would need a diagram to illustrate this idea. And perhaps now you will really begin to understand why it is that I emphasize definition so much in chapter one, because I expect you to be able to take language like this and produce the diagram that corresponds to that. And you can only do that if you know the relevant definitions. And of course, also how to draw and label diagrams. So we need a pair of vertical angles, and we know that we get vertical angles when a pair of lines intersect. And so let us label points so that we can actually name these vertical angles. And I don't know, how about an M for the point of intersection, and then A and B and C and D. Okay. So notice what we've done. We have produced a specific instance of what this theorem says. Okay, and then when we actually give the proof, as we'll see tomorrow, really, or in the next section, we'll talk about this specific diagram. Okay, and then step 3, as I said before, was the word given, followed by the given of the conditional that we're asked to prove, as it specifically refers to the diagram that has been produced. And then prove, followed by the conclusion that we wish to prove again, and that will refer specifically to the diagram that we have produced. Okay, so let's put all of this together. I've talked in general too much about this, so let's do this start to finish. So let us say that we wish to prove that the sum of the angles of a triangle is 180 degrees. Okay, so what is that in conditional form? Now, like I said, later on, sometimes we won't pause to give the conditional statement, the conditional form of the statement we wish to prove, but I think it's helpful here at the start, so we'll do it. So if, how about this? If we sum the angles of a triangle, then that sum is 180 degrees. Okay, so the given here is this, is that we have the angles of a triangle, and of course we form their sum, and we wish to prove that that sum is 180 degrees. Okay, so what comes after the conditional is a diagram. So we need a specific diagram to illustrate what it is that we wish to prove. Okay, so let us produce a triangle, and let us label it so that we can name the triangle that we have drawn. Okay, so we know how to do this. Typically the way that we name a triangle is by its vertices, and those are points, so we use capital letters. So there's a particular triangle ABC. So what is the given here? Well, the given is really just that we have triangle ABC. Okay, that's all that we need to be given in this particular statement that we wish to prove. And what do we wish to prove? We wish to prove that the sum of the angles is 180 degrees. So what is that? It's the sum of the measure of angle A plus the sum of measure of angle B plus the sum of the measure of angle C is 180 degrees. Okay. Now, of course, the next step after this would be to actually give the proof, and we won't be ready to give proofs of theorems like this, angle sum theorems, until a later chapter, but this is how the proof will be set up in that later chapter. This is precisely how it will be done. Okay, so let us show how it is that we would set up another particular proof. Not to give it, of course, it will be for a later day, but just to get started with the setup. Okay, so prove that equilateral triangles are equiangular. So in conditional form, that would be if a triangle is equilateral, then it is equiangular. Okay, so there's the conditional that we wish to prove. Okay, so what do we do now? Well, we draw a picture. Okay, so we wish that picture to illustrate, we wish that picture to illustrate that we have an equilateral triangle. Okay, so So we have a triangle ABC or DEF or XYZ or whatever, it doesn't really matter. Okay, but in this case, unlike the previous theorem, we have more than just a triangle. We have specific information about that. That is, it's a specific kind of triangle. It's an equilateral triangle. So let us illustrate that into the diagram. And we know how to do that. We use hash marks, of course. And then let us state the given. Okay, so triangle ABC with AB, oops, sorry, with AB equal to AB equal to BC is equal to AC. And a sort of run-on equation like that says that all of those quantities are equal to one another. So we have a triangle ABC with AB equal BC equal AC. That is its equilateral. And then what we wish to prove, of course, is this, is that the measure of angle A is equal to the measure of angle B is equal to the measure of angle C. That is, all three angle measures are equal to one another. So that's how we would set the proof up. Okay, so the assignment that I will have you to do today will be one in which you set up proofs of various kinds. You will make use of your knowledge of definitions of terms and how it is that we draw diagrams and label them. And you will set your proofs up like this. That is, take the statement to be proven, and if it's not conditional, write it in conditional form, draw a picture, draw and label a picture to illustrate, then state the given and what you are to prove, and make those refer specifically to the diagram that you have produced. Okay, so that is the assignment for today. And then tomorrow we will actually start to give the initial proof set for the class, and those will be angle proofs. So we'll prove, for instance, that linear pairs are supplementary, that vertical angles are equal, that perpendicular lines do in fact form four right angles, and some others as well.